Materials supplied by Microsoft Corporation may be used for internal review, analysis, or research only. Any editing, reproduction, publication, rebroadcast, public showing, internet, or public display is forbidden and may violate copyright law.
Hi everyone, it's my pleasure to reintroduce Paul Smolensky to continue with his talk series where we discuss making neural networks understandable. And I just wanted to do a preview that we're going to do part 3. Paul has agreed to do a part 3, which will be most oriented towards linguistics on this coming Friday. And thank you for listening, and we really appreciate your taking the time to give this extended talk series.
Well, I appreciate the very valuable interaction I've been getting. Although I had said that the talk part 3 would be addressing linguistics, I should really have said language. It's not so linguistic-y. Okay, so last time I mentioned that there were 2 goals that I had when I came here. One to do with reverse engineering, trying to understand networks that exist, and I'll come back to that towards the end. What I'll talk most about is the goal of engineering networks which are built to be understandable and to hopefully, in virtue of their greater interpretability, allow us to program into them useful constraints that will allow them to perform to a higher level of linguistic competence in virtue of being able to process discrete combinatorial structure, which is not really inherent in the neural medium. Okay, so this is the, I think pretty much the same list I had last time. I think we got to item number 2 or something. We'll see. Maybe we'll get farther this time. The challenge, you may remember, concerns trying to unify 2 approaches to artificial intelligence or cognitive science. And those are stated here in terms of hypotheses. One about the value of symbolic computation as a means of description of cognition and intelligent behavior, and the other one, the value of neural computation for the same types of purposes. And the approach that this system called gradient symbolic computation takes is to posit a cross-level mapping to view H as describing a more macroscopic level of the same system that N is describing at a more micro level, and to link the 2 by an embedding mapping called psi here, which maps symbolic structures into a discrete subset of the vectors in the neural vector space. So here was the picture I put up last time to remind you about analogies to other fields where we have macrostructure emerging from microstructure. The mapping psi is what links this kind of description to that kind of description. And you remember the idea is that to try to design networks with the capability of computing functions which on one level of description are taking structured symbolic inputs like perhaps trees and mapping them into other structured objects, perhaps propositional representation of the meaning of the sentence, and to compute that function not by operating on the symbols in an explicit way, but by taking advantage of this embedding to put the input into the vector space of neural network states, apply neural network computation to produce an output, which can then be reinterpreted symbolically if desired. And so I'll say some words about the kind of functions F that have been shown to be computable in this way. And those theorems are the formal arguments that I can offer that this computational system I'm describing really does provide a kind of unification of these 2 quite different approaches to modeling intelligent cognition. So I also mentioned that the result of this particular way of doing the embedding is a kind of intermediate level in which tensors figure prominently, so call that tensorial level. So we can add a kind of intermediate hypothesis about the value of gradient symbolic computation described at this level for characterizing the knowledge and processing in intelligent systems. Okay, so now there's an important step which I would love to do right now. This is where it belongs, but given my experience last time, I fear that we might not get beyond it. So I've decided to postpone it, and I hope we will get to it at the end instead of at the beginning. But part of it, it has to do with characterizing neural computation as involving not just activations in neurons, but representations that are in some sense sub-symbolic, where the conceptually interpretable entities, and talk is all about interpretation, the interpretable entities are distributed through activation in extended parts of the network. So that's a very important part of the whole story, but I propose to postpone most of it. I will mention a few of the reasons for distributed representations centrality, but leave the most important one in my way of thinking about it to the end. So for engineering purposes, distributed representations provide important similarity relations. So if you have one unit dedicated to one concept and another unit dedicated to another concept, and all the concepts have single units dedicated to them, then all concepts have zero similarity to each other. That's how local representations are. And on the contrary, if an activation pattern is what is encoding a concept, then two different concepts will have similar or more similar or less similar activation patterns, and that similarity will play an important role in determining how what's learned about one of these concepts would generalize to the other. There is the fact that you can get many more distributed representations than you can get local representations in a set of n neurons. There's only one representation per neuron in the local case. Distributed representations afford the opportunity to pack the n-dimensional space with more than n conceptual entities using distributed patterns to encode them. Okay, and then for reverse engineering, it just seems to be a fact that the representations that are learned by networks in their hidden layers and the representations that we find in the brain have a very significant distributed component. Rarely you do find individual neurons that can be given a conceptual interpretation, but that is falls far short of providing enough understanding of the system to explain how it functions and why it succeeds and why it fails when it does. So understanding neural computation as trafficking in distributed representations is an important for understanding systems.
There are certain local representations like grandma cell. So how does the theory reconcile the possibility that there is maybe the small number of neurons that we need to have local representation?
Well, the principle is that the design of networks must be such that distributed representations are possible. But local representations will also be possible, and in some senses, perhaps for some purposes, preferable. But the local representations are a special case of distributed representations. So if you're set up to cope with distributed representations, then you can specialize to local, but the reverse is just not true. Okay, and so there is a fundamental aspect of neural computation in my view, and what I'm postponing is a very general symmetry argument, which leads to the conclusion that neural computation must always allow for distributed representations, as I just said. And I propose to skip that. Let's see if I can skip it. Okay. Well, that didn't work, so let's back up here. Okay, so I'll move on to the next topic now. And just review the actual proposal for how to embed symbolic structure in distributed activation patterns in neural networks, what this psi function looks like. So just a lightning review of what we went through rather slowly last time. We'll be using patterns of activation in which the individual activity levels can be thought of as being the elements of tensors. And an nth order tensor is characterized by an n-dimensional array of real numbers. There will be n subscripts or indices to distinguish these members from each other. The two basic operations that we talked about are first, the outer or the tensor product, which increases the order of tensors. So if you multiply A and B together using the outer product, you get a tensor of order n plus m, the sum of their orders. Whereas contraction decreases the order. So contraction is tagged to a particular contraction operation is tagged to a particular pair of indices in a tensor. So to contract over the specific pair ij in a tensor that has rank at least order at least 2 is to take the ith and the jth indices and replace them both by q and then sum over all the possible values of q. And that's what's written out in a painful way here. So it takes two indices, sets their values equal, and sums over all the possibilities. So special cases of this that are very familiar is the dot product when the two tensors are just first order. The matrix product when the two tensors are second order. That involves taking two indices, the second index of this and the first index of that, which means the second index of the tensor and of the outer product and the third index of the outer product, setting those two equal to each other, that gives us the, and summing over all the possible values gives us the matrix product. But whenever I write two symbols like this next to each other, I'll try to be consistent about using this open face for the tensors. You should not interpret that as a matrix product unless it's explicitly described as a matrix product. Otherwise, everything will be outer products because, as I told you last time, I'm experimenting with omitting the outer product sign, which otherwise would be covering the page. Okay, the general concept of inner product with respect to two indices involves basically taking two tensors, A and B, taking their outer product, and then contracting over two indices, one falling within the indices of A and the other falling within the indices of B. The matrix product is one case of that. But we have use for inner products more generally. Because the symbolic operations that these tensors are embodying will use the outer product to bind information together, and will use inner products to separate, to extract, unbind symbolic elements from one another. So some of the examples that we looked at last time are shown here. So a simple case of a kind of slot with a name filled by some element is represented. The representation of that binding together of this role and this filler is achieved by the tensor product. So if the agent role corresponds to the tensor A and the element individual J corresponds to the tensor J, then it's their outer product that represents this pairing, this ordered pair, essentially. In the case of a graph, we have two nodes linked by some labeled arc, let's say, a relation R. And again, we just take the outer product of the tensors that encode the individual labels on the nodes A and B, as well as the label on the arc that joins them. So writing these tensors here in the simpler way, we just take the three-way outer product of those three tensors to encode that one triple or one edge of a graph. And very analogously, if we have propositional type representation, we have a relation expressed in terms of two arguments for a binary relation, then we would take the outer product of three tensors, one for the relation and one for each of its arguments.
Yes,
And
so
for the higher,
the difference between the two is that one is undirected, the other one is directed.
they're both directed in the sense that Rxy and Ryx are different tensors.
That can be, I mean, the first one, no link, no binding, can also be interpreted as a relation one. Very often you say that.
Yeah,
Okay,
these are just two ways of writing the same thing.
okay. So this is a rotational convenience. You could like swap.
Yes.
If you actually do the real tensor computation at the end, sometimes you don't know which order it is, because once you do your neuron are doing all this computation, you just get the tensor. So you have to stick into one consistent definition there in order to interpret the result.
Right, that's right. So a tensor product representation brings with it a discipline for interpreting the different dimensions of the tensor, how they are arrayed in the activation vector or activation pattern.
An example to differentiate between node link node versus relation binding. So at least you see why there is a need to have two different ways of.
There's no need to have two different ways. This is just a bunch of examples, things that are familiar from symbolic
I see.
descriptions in AI and how we encode them.
I see. Okay.
That's all.
Okay.
In the project that there are two projects that I will describe very briefly if I get there, and one of them is using this notation and one is using that notation, so I wrote them both out. Otherwise, it's kind of redundant. Okay, and here's an important point that came out in discussion after the lecture with Lee, in fact, and so I wanted to emphasize it on this review, that another type of a tensor product representation uses something you can think of as absolute positions within a structure to individuate the symbols that comprise the structure. So in this case, what we're talking about is a string, AXB, and X, just the representation of the X in that string, is one way of doing that is by having a vector that is associated with the role that it plays, the position, which is the second position in the string. So R2 is a variable whose value gives you the second position in the string. And in this case, its value is X. So the outer product of this vector R2 and X is the tensor that encodes the single constituent X within this string. With trees, you have a similar story, but now the set of positions is recursive. So in a structure like this, where we have this tree, if we want to talk about the X in the middle of this one, then we can talk in the same way in terms of tensors that encode the positions within the tree. In this case, I tend to label them with bit strings. So R01 is the position which is the left child, 0, of the right child, 1, of the root. So the path to the root is indicated by these bits in the name of the role. And it doesn't matter whether you do the R before the X or after the X, as long as you're consistent in carrying it out. Yes?
So I noticed that you have agree for the A and B, so do you mean that it's for later on you need to substitute the exact tensor of A and B And that's just a simple, that's just a representation that if this is a tree, you need to use this as the representation of the x. But later on, if you have real value of tensor for a and b, you need to put a and b somewhere to use together with this. I'm not sure what's the meaning of that gray, the gray letter a and b here.
Hold on till the next slide, which is just one line away. And the fact that the positions in trees are recursively related to each other can be captured, and has to be if you want things to work out to do recursive function computation, by taking a role like this one, or position, 0, 1, left child of right child of root, and expressing it in turn as an outer product of a vector that represents left child and a vector that represents right child, in the particular order associated with the path to the root. So this in these I neglected to mention that I've been dropping the explicit encoding of the order of the tensors because we were just talking about first order tensors all the way down here. But now, in order for us to be able to talk like this, we have to say that we can start with first order tensors, vectors, for the primitive roles of left child and right child, and then generate an open-ended, limitless set of additional tensors that are used to encode all the positions below. But their Gesundheit, their order increases as you go down the tree. So this second level has second order
But that's
tensors.
marked already, right? Because when you say 0, 1, they already marked that it's
Yes, you
left or
can
right.
infer that the two from
I
the.
see. So this
from
is
that.
still redundant.
Yeah, it's not necessary, and I may not carry it through. I'm not sure if I remember, but I at least wanted to point it out here because it's the first time that higher than first order tensors are being used in the examples. Okay, so binding is done by the outer product. I will. Oh yeah, so the point that I wanted to emphasize, and just skip yet again, is that in order to encode the structure, the symbolic structures like strings and trees in vectors, we make explicit the different roles that symbols can occupy. Those roles are normally implicit in the way we draw the diagrams, in the way we string the symbols together in a string. So it takes a little getting used to sometimes to be making completely explicit the notion of role within a structure, because that's so often the job of a notation is to hide that, make it implicit. But we make it explicit in order to carry this forward. All right. So outer product is used to bind together symbols and the roles that they play in a structure, or symbols to one another if they're bound together in the structure. And the remaining operation that we need is the means for putting together multiple constituents to give the vector for the whole, which is what you were asking about with the gray letters in the previous tree example. And it couldn't be simpler. It's just done by addition. So if we have a two-variable structure like this, then each one is represented the way I just said, but we add the two together to get the representation of the structure as a whole. If we have two arcs, we add together the triples that we talked about a moment ago. If we have three letters in a string, then we add together three tensors, each one encoding a single symbol in its location. And for the tree, it's the same story. Here we have three constituents to add together. We talked about the X one, but then here are the other two. They get added in. And by using the recursive property of the definition of these embedded roles, that this role here is in fact the outer product of two primitive roles for left and right child, we can observe a nice recursive property of this representational scheme. So once we expand this out into its primitive parts, we can factor out the R1 that these two have in common. That is to say, these constituents are both on hanging off the right child of the root in this position. If we factor out the R1, then we get this expression here for the tree. And that is nothing but the embedding of the symbol A bound to the left child position, and the embedding of the tree structure now, not atomic symbol, but the embedding of the tree structure bound together with the right child role. So any binary tree that consists of left child P, however complex that subtree might be, a right child Q, the encoding of that will be expressible in terms of the embedding of P itself, the embedding of Q itself, and then the two roles that each get bound to when they're combined. Okay, so I call that a recursive representation because it obeys this equation here. Yes?
Is this conjunction approximate, or do you take care of how you find all these tensors so that it's exact?
In the process of constructing a representation from a symbolic structure, it's exact. In the process of reverse engineering, we're going to have to make do with approximate summation. But
So how do you ensure that the first example, for example, how do you ensure that that you get a vector that encodes truth if agent is J or patient is K, rather than some kind of fuzzy combination of the two when you're adding things?
What's encoded in my way of thinking about it is the conjunction of two propositions, one asserting that the agent is J and the other asserting that the patient is K.
But how do you? Okay, so how do you enforce the conjunction? I guess I don't understand how. I mean, this is an assumption that of the model, but how do you know that what you're going to get is a conjunction from this? It doesn't follow exact. I mean, it's not clear to me that you can do it with an addition.
Okay.
I mean, I can imagine how I would make it happen by using proper vectors for agent and J and so on. But if they're not orthogonal, or if they don't have certain properties, if you're learning from the data, then it's going to be some kind of a fuzzy conjunction.
Well, yes. If we're learning these from the data, then all bets are off as to what extent these summations and the outer products themselves are going to prove useful as a description of what's been learned. In an unconstrained system, I mean. We can build systems to be constrained so that they will always use addition and outer product operations, and then we know that they're exact. But for reverse engineering a generic network that has not been built to specifically use tensor product representations, then all of this will at best be an approximation to what we'll find in there, I'm sure. I did want to point out that let me use the term proper to describe a tensor product representation in which all the vectors encoding symbols and roles are linearly independent of one another. And so at the very least, what we can then say, whether or not you're convinced that this summation can encode, that it would encode conjunction as opposed to something else, we can at least say that this is the result of this is unambiguous as to what is bound to agent and what is bound to patient. And then, so this is the world in which the theoretical work that I have done takes place, the world of proper tensor product representations. Fortunately, the world of Microsoft is different because we can't afford to have as many units as it takes to have linearly independent vectors for all of the symbols.
Right, and that's the other question that I was kind of meaning to ask maybe later, but maybe now is the time. A lot of this, I'm sure that theoretically it's going to be nice for analysis, but computationally, it's a very inefficient way of representing certain computations if you do it naively. So do you have, do you revert back to later to not really expanding and then projecting, but actually computing your inner products directly in implementation?
So the context of what defines an acceptable kind of computation that I've worked in is implementable in a neural net using neural operations. And so the notion of efficiency is rather different because you have parallel computation of the multiplication and addition operations available to you. And I have not explored what it takes to do efficient emulation of these computations using digital architecture instead. But that's certainly also a critical thing now. Yes?
In the recursive tree, one, you're adding tensors of different dimensionality, right? Is that a problem?
Well, what you have to do is you have to have a big vector space in which these are sub-vector spaces. The subspace of order 2 tensors, the subspace of order 3 tensors, all together in one big happy vector space. So in that sense, it's addition within that bigger space that's well defined. Sometimes,
So any tensor that's of less dimensionality, you sort of boost it up to this high dimensionality before doing the addition. Is that what
in
you
some
mean?
sense, yes, that's right.
But how do you
Because-
decide like what slice of you just kind of arbitrarily pick like a corner of the space that things slide to when they're less dimensions?
Yes, I guess that's a way of saying it. Yeah. So you have the basis for the space as a whole is all built up by multiplying together these R0s and R1s. And so if we just embed R0 and R1 themselves in the large space, then that picks out a two-dimensional corner where the depth 1 trees will live, and so on after that. It's all ripped off from particle physics without change. Multiple particle systems consist of a direct sum of spaces for 3 particles, 4 particles, 5 particles. And so in the equation here, let's see. No, this equation here. Right, so when we add together these tensors of different order, there's some references. The symbol here could also be the direct sum symbol instead of the regular sum symbol, because we are talking about adding elements of 2 different subspaces in the bigger space. So if you are happy with thinking about it that way, that's also a perfectly legitimate way of thinking about it. But I didn't think it was worth going into that, but I guess I just did. Okay, further questions before I go on? We use outer products to bind together symbols to each other and to their roles in structures, and to extract information from a tensor that encodes multiple constituents, to unbind roles and figure out what is the symbol in the second position in a string, we use the inner product. Just for convenience, I'm going to assume that the vectors encoding symbols are not only independent, that they're orthonormal. So they're orthogonal to each other and normalized to length 1. And we'll make good on that asterisk at the bottom of the slide to back off from that a little bit. Okay, so if we take the example of strings, if we want to extract the symbol in position k within a string, then what we want to do is unbind the vector, the role rk, which was used to bind that symbol originally into that position. So here's our representation of the string AXB again, called S. If we want to find out what's in the second position, we need to take the inner product of S with the second role vector. That's the vector. That's the role we're trying to unbind. So we take an inner product of these two, and the inner product is a linear operation. So the inner product with S is just the sum of the inner products with all of its constituent tensors. And because of the orthonormality assumption, R2 and R3 are orthogonal, so their dot product is 0. Similarly here for 2 and 1. And the only one that doesn't get wiped out in the inner product is exactly the role we want. R2 dot R2 is just 1. The vectors have been normalized. And so we end up pulling out exactly the filler of that role in the structure as a whole, indicated here. And exactly the same thing works with the trees. Exactly the same thing works if we're trying to extract information from the graph kind of representation I showed earlier. But it plays out a little bit differently because we don't have positions in the graph. We're not using that notion of role. We're identifying the nodes in terms of the positions they play within these local three-way relationships instead. So the kind of question that we want to ask in this case is, what is at the tail of an R edge from A? That is to say, what is related by R to A, according to the graph? So here's the representation of our graph. It's representing the two triples. And if we take the product of the two bits of information that we're using as our retrieval cue, the relation R and the atom A, take their outer product here, then that is what we want to use to probe the tensor for the graph as a whole. So that inner product will, for just the same kind of reasons as we saw above, wipe out all of the constituents except those that in fact have AR in them, and that will pull out just B as the result of. Okay?
So for the other type of relation finding, the same thing will happen if R is on the left hand side. So this is R in the middle. So,
Right.
okay.
Yeah. So we need to just keep our discipline that R is in the second, that the second dimension of our third order tensor is where the relation goes. We could have chosen it to be the first one instead. And then we would have RA here instead of AR as the probe. Okay, so as far as the asterisk is concerned, so in a proper tensor product representation, what we have is that the vectors are linearly independent. They aren't necessarily orthonormal. But the mere fact that they are linearly independent means that there exists another set of vectors which we can use exactly in this way. So instead of R2, we use R2 plus in that case. Instead of R01, we use R01 plus. So these dual vectors have exactly the property needed to make this calculation go through, namely their dot product with all the other roles is 0, and their dot product with their own corresponding role is 1. So RK dual dot RK is 1, RK dual dot any other RL is 0. So all the calculations go through as before.
So what do you want to just dual vectors? I kind of forgot your mission. So this is just short notation for the things that you talked about earlier, or is it?
Well, we can't do this. We can't unbind by taking the dot product with the vectors that we use to do the binding if those vectors that we're using to do the binding are not orthonormal.
Oh, I see. Okay.
So if they aren't orthonormal, then the vectors that we want to use to do unbinding are not identical to the vectors that we use to do binding.
So in that case, it's an approximation. You want to cancel out everything to be 0, so you can pull out the right thing. Or
So either you use the exact unbinding vectors here, which will make the calculations go through exactly the same, and you'll pull out exactly the right filler for the role you're unbinding. If instead the vectors are approximately orthogonal in some sense, and you don't use the exact unbinding vectors here, which are the dual vectors, instead you stick with using the original role vectors to do the unbinding, then you will get some noisy approximation.
There wouldn't be orthonormal to begin with, because you can always orthogonalize everything.
Well, one of the big advantages of distributed representations is that we have similarity relations among the elements, and so we don't want to lose the ability to use that. We want to take advantage of that. Yes?
So your formalism supports conjunction, but what about disjunction? Does that make sense here at all? I mean, suppose ARB or ERB.
Yeah. Well, I would need to go up a level and put the logical structure of these expressions in a form in which we're actually conjoining clauses together, but the clauses include things like disjunction signs, and then the operations have to be the ones that are appropriately interpreting those signs. It won't come for free in the same way that this low-level conjunction comes for free. It may be a little misleading to even use the term conjunction for this, but certainly it's true when you write down a graph, you are saying that this link is there, and this link is there, and this link is there. That's what the semantics of the picture is, right?
The tensors. They're not things with value true false, they're things with lots of values.
Yes. Right, and so operations on them could produce zeros and ones, but they themselves have some kind of richer content, is the idea anyway. So what does gradient symbolic computation get from tensor product representations? It gets a new level of description where we can talk about where the data are these tensors, as opposed to just a bunch of numbers which are activity values, as opposed to a bunch of symbols in some structure. We have tensors as a kind of intermediate level. And we can derive techniques that apply to arbitrary distributed representations, which are interpretable in the sense that we can understand exactly what the data is representing. We can build knowledge into networks that process these representations because we know how the data are represented. We can construct programs to do particular calculations that we want, and I'm going to give you some illustrations of that. We can write grammars that will allow networks to pick out the tensors which are the embedding of the, let's say, trees that are generated by the grammar or evaluated by the grammar. And of course, you also get massively parallel deployment of this knowledge, as I mentioned a moment ago. So this is all intended to be construed as neural parallel computation. For cognitive scientists, we get a set of models that are really more about unconscious automatic rapid processes than they are about deliberative ones. So reasoning about disjunction is something that we do deliberatively. So that would be handled within a larger architecture in which there are inference processes that are built into network machinery. Okay, so
the assumption is that unbinding is done automatically by the brain, right? Because all the neural computation eventually result in vector. So somehow unbinding has to be done unconsciously.
yes,
Automatically,
well,
so that-
the main thing about unbinding is that I don't think the brain does it.
No?
We do it when we try to interpret the states of the brain. But so that was a gross exaggeration, but the point is that whereas straightforward implementations of sequential processing and so on would have us unbinding all the time before we do anything. And I think it's the exception rather than the rule that unbinding would be done.
So come up with half a second the number. So what's the number? The synaptic delay or something in the previous slide.
It's just a very crude characterization of sort of the threshold of consciousness and what kind of processes are not accessible to it. Okay, so I want to give you some examples of programming with these tensor product representations and what kind of functions can be computed as a way of just arguing that this isn't just any old way of packing of taking vectors and giving them names like this tree, that tree, this tree, but rather it's a form of vector encoding in which neural operations can do what we want in terms of computing functions for which those symbolic structures were posited in the first place. So next time I'll talk about grammars, and I won't talk about that today, but I'll talk about something more straightforward. And we're going into the dark land of super nerd slides for just a little while. And hopefully it will give you a feeling for how what I mean when I say that these networks can be programmed. So suppose we have a function that takes a sentence of a certain structure and maps it into an interpretation in the form, some logical form like this. I want to construe that really as a mapping between binary trees, and here's a toy binary tree for something that we can pretend is a passive structure that gets mapped into a binary tree encoding of this proposition here, one of many ways of doing it. But having chosen this particular way allows us to write this function down in a Lisp-like notation, extracting the right child of a node, extracting the left child of a node, putting two children together to form a mother node from them. Those are the primitive operations for tree manipulation here. And in terms of them, we can write down an expression for this function. And no matter how big P is as a subtree, no matter how big the agent subtree here is, this function will do the right thing and put all of A here, however big it may be, and all of P there, and so on. So here is a network that computes this function in the sense that this group of units is the input pool, and the activation pattern here is the embedding using the tensor product isomorphism of this tree, with some selection having been made for what activation patterns correspond to R0 and R1, and the symbol A and symbol aux, and so on. Actually, we don't need A, we just need aux. And so having made some choices about what numerical patterns are going to be used to embed the primitive bits of this, then it's all assembled using the tensor product schema I just laid out. And so here is our input to the network, and this output pattern stands in the same relation. It's the embedding of what we hope will turn out to be this. And the operation from the input to the output is nothing but a matrix multiplication. This is a linear network, simplest kind of connectionist network you could have. And so the implementation of this function is just a multiplication of the input by this vector of weights here. Now, we can actually write down what the weight matrix needs to be. And here it is. So having this expression for the function in terms of primitives of binary tree computation, we can write down an exact expression for what this matrix looks like. And this is really the upper left corner of an infinite matrix, or an unboundedly big matrix, because each of these things are actually very, very simple but unbounded matrices that implement extracting the right child and extracting the left child and stringing together two children. So despite the fact that we have a distributed representation in which members of this tree are mushed together, we know exactly what weights it takes to produce exactly the right mush to embed the output that we want.
So the way to derive that W is based upon the principle you talked about earlier, unbinding. Usually the unbinding operation to get that formula.
Yes, essentially, yeah. So essentially what this does is take an inner product with the dual of the roll vector for binding the right child. That's right. Yes?
Will the W be unique, given the input and output?
This W, the total weight matrix?
Right.
Well, I guess if the I don't know. I think so. What's learning?
This one doesn't require learning for a specific example, but if you have many examples, you won't be able to fit that directly. So at least you do least square fitting, you can get optimal W. That gives the minimum error when you have many examples. Is that the way you think about it? For specific example, you don't need to learn one.
Well, it's an interesting question whether there's a learning algorithm such that if you give it a whole bunch of pairs that are actually instances of this mapping, that it will learn a matrix that does it. I can tell you one thing which will help a lot, which is that there's a theorem that says that recursive functions all have a certain, well, at least ones in the class that include this, all have a certain form in which they are the product of some very simple, it's really an identity matrix, but it's infinite for all of the depths of the trees, times some smallish matrix which characterizes the particular function that you're implementing. And so a learning system that was built to incorporate that structure would be able to generalize from what it observes at shallow depths immediately to what should happen at deep depths. So what it really is building in a kind of translation invariance within the geometry of the tree. Like a visual system that has translation, a learning system that has translation invariance built in somehow, you get automatic generalization in the same sort of way here. But let me just
say that if you actually want to reduce the dimensionality of W, then you need to do learning so that you can figure out what is the W that give you the minimum error given the constraint on the dimensionality of is it?
Yeah, I mean, I haven't worked on questions like if we don't have linearly independent vectors for all of our roles in the tree, what's the best matrix and how would you possibly be able to learn it?
Example, what is the dimensionality of W? I think I get a little confused here. So it's high dimensional, it's not just two dimensional the way you draw.
So,
So
if you mean what order tensor is it?
the other thing.
Yeah, I mean it's operating, it's multiplying tensors to produce other tensors. So it's, but it can, we can write down this expression itself characterizes essentially an infinite matrix, which can deal with trees of any depth.
What is W comes actually does? Is
Uh,
it just is it just the W comes, W sub comes?
It constructs a tree by putting together the left child and the right child to create a binary tree with those constituents. So you take W cons 0 and multiply it by the tensor that encodes what you want the left child of the new tree to be, and add to that W cons 1 times what you want the right child of the new tree to be, and then you get the new tree with the right children. But it has sort of two parts, cons 0 and cons 1, because it has two arguments, essentially. Okay, yes, thank you. Thank you. These are actually matrix products here. Yeah, should say that. Yes?
So if I have the sentence, few leaders are truly admired by George Bush,
Okay.
is it the same W? Because you've kind of hard-coded that you need this aux, feed, and buy in this particular configuration. Now, if I insert something,
Right.
it's a different tree.
Yes. So the function I started with here was not, will not generalize to that kind of case. If we could write a function using these operations that did, then we could correspondingly build the network that would compute it. Yeah.
So I'm sorry, I think I've totally gotten confused here. So before the representation of the tree was a tensor of dimensionality, kind of like the depth of the tree or something. But now you're saying there are 2D matrices that are infinite in size. So there was some sort of transformation I missed, or
Okay. So
sorry.
so here's what is potentially quite confusing about the picture. It's totally because of the two-dimensionality of the page that I have these units arrayed in 2 dimensions here. So these are the elements of a tensor that has high order. The order, as you say, determined by the depth, beyond which everything is 0. So you could array it faithfully in many dimensions, or you could just linearize it to one long string. And maybe doing that latter would have been less misleading, because there's nothing too-ish about it, actually. But anyway, this is the tensor that we've been talking about all along, that you get by binding these symbols to their roles in the tree. That's what this is.
Okay.
And then this is an operation that maps one of those to another one of those.
But the operation is just a 2D matrix multiply? Is that, or maybe I misheard?
If you just imagine flattening this tensor out to one long string of numbers, and similarly over here, then we just have a 2-dimensional matrix for taking the one string to another string.
Okay, so there's a step where you've sort of flattened the tensor into 1 or 2D in order to do this.
Yes.
Not just for the diagram, but
Well, just for the diagram, really. So really, you have linear transformations from the space of tensors to the space of tensors is really what this is supposed to be trying to depict. So linear transformations from, a space which may have high dimension to others. We can talk about them without any confusion, but we can't necessarily draw them in such a nice way on the page. I mean, if you were to see the actual equation that this is depicting, what you would see is that W would have huge numbers of indices all over the place. It would have huge sets of indices, one for the inputs and one for the outputs. And so there would be no two-ness about that either. Well, except that it's mapping from input to output, and so that is 2 elements that are being related. It's only has one input, one output, so it has 2 sets of indices, one for the inputs and one for the outputs.
The question is, once you have the output space, which has a tensor structure inside, so how do you unbind it? For example, once you have the output, how do you know that that is a tensor representation of the knowledge of Admire, George Bush, the two leader versus some other representations of the knowledge?
In setting this up, some choice was made about what vectors to use to encode left child and right child. And in theory, you could make one choice for this embedding and a different choice for this embedding. I don't think I did. I used the same choice for both. But relative to the choices of the embedding of the primitive roles, left child and right child, then you can unambiguously take inner products galore with this vector and R0, R01, R0001, and each one will pull out what fills that position in the output tree. And so if you were to take the inner product of this thing with R0, you would get the activation pattern for the symbol V. If you did the inner product with respect to the R1 vector, what you would get is a pattern that encodes this tree here, the right child. And then if you took that and took an inner product with R0, then you get a pattern for this tree. And if you kept doing that, you would eventually get down to the atoms like Few and George and so on that are embedded inside those constituents. You guys can duke it out.
The R's from the original passive sentence through the matrix to get the R's in the output.
R's?
So if you apply R0,
Yeah.
you're going to get, or R, which one is that? R1, 0, you're going to get V, right?
Yeah.
If you multiply by a matrix, you should presumably be getting R0.
Yes. 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 That's what all these guys are in the business of doing.
So if your input is an N, tensor and the output is an M tensor, and W is an N plus M tensor, or whatever tensor. But there's lots of ways of contracting an N tensor, an M plus M tensor to an N tensor. So is it just you set things up with formalisms, you just take the first N coordinates, and that's the contraction you do with this formalism to get your output?
I think so. Why would you do anything else?
Because there's, I mean, it's not unique, right? I can contract it on any pair of indices I like and get an N tensor out. There must be something that's having you decide which ones to contract. No formalism.
Yes, I guess it's true that. So let me back up to something I said before. So the theorem would say there is a linear transformation from the space of tensors to the space of tensors. Okay, and there's no unique way of writing down a linear transformation. So you need to make choices if you're going to do that. But as far as I know, it's no different from the choices that you would make in doing that in other contexts. Yes?
Does the math work through for any choice of roll vectors as long as they're orthonormal, or did you have to pick, like, carefully choose them to make this work?
As long as they're linearly independent, we can do this, because we can define these in terms of the dual vectors, which will compensate for any lack of orthonormality that there might be. So this function here is linearly neurally computable. Here is a linear neural network that computes it. And so there are results characterizing bigger and bigger sets of functions that are linearly neurally computable. As far as I've gotten so far is the class of primitive recursive functions, which can be defined in terms of one another by recursions like this. We can, if anybody's curiosity is piqued, we can come back to that. But let me try to just, at a higher level, characterize what's going on in these results here. So first of all, there is a single-step operation, that is to say a massively parallel operation from the distributed encoding of the input to distributed encoding of the output. That's what it means to be computing a function. And we are implementing them in the simplest kind of neural network here, linear transformations. Primitive tree constructing and tree constituent accessing functions are implementable as linear transformations. So we can realize them as matrix multiplication once we make the right choices about bases and all of that. An arbitrarily complex composition of these operations, tree constructing and tree constituent accessing, an arbitrarily complex composition of these is still just a single linear transformation. So a linear network can compute the set of recursive functions that is the closure under composition of the primitive tree operations, including the one example we looked at. And to implement a recursive function that's defined by a primitive recursion, an equation, a recursive equation in this class of primitive recursions that I showed briefly, what we need to do is take the corresponding recursion equation for matrices relating the input vector to the output vector and solve those recursion equations for a matrix. And then we have the way of computing the recursive function. So this is a slide about that, but I'm going to skip that.
So, quick question. So, everything I understand so far, the operations are all linear
So far,
in this model. Is it going to stay that way? I'm just curious.
No.
It looks like all the
We're going to get to
rest
this
is
point.
structure.
We're going to get to this point right here. And then we'll be talking about multilinear rather than linear operations. But everything is stayed in the multilinear. They're sort of like polynomial functions. Too bad Ronnie's left. What?
If you bind politician to leader, you can multiply with these matrices.
If you bind
Right?
politician,
If you do the outer product between whatever your representation for politician is, whatever your representation for leader is, I don't mean as words, but as categories. Like leader
Oh.
might be a word, politician might be a category.
Okay.
And you bind that, and then you can multiply again with basically the same matrix.
Yes.
So then you end up with something that doesn't replace leaders with politicians, but it actually has all of that information in the output. It has that relation, plus it has the information.
Yeah,
of
that's
politicians,
interesting.
leaders,
I
and
think
so on.
I think that should be doable. Yep, that's interesting. Yes. So the example that I looked at involved copying of symbols, but the very first statement about the class of linearly computable functions is that transformations that leave symbols in place but change one symbol to another, and then what you're interested in is changing one kind of symbol to another kind of symbol, I guess, one that is somehow refers to a category and multiple members and such. Yeah, Chris. All right, so let me see. So the next item here is an example from cognitive science about what happens when you take advantage of the similarity structure of distributed representations for the roles of symbols in a structure, specifically the roles of phonemes in syllables. But we are, again, running very short of time, so I wonder so shall I keep going? Or shall we switch into a more open discussion mode? What's your pleasure?
Well, I have an open discussion question. So far it seems as though every predicate or every concept has to have its own orthogonal vector, or at least linearly independent vector or something else. Is that going to hold throughout the formalism? So you're going to have these giant directional spaces, which everything is sort of multilinear or linear.
That's what things have looked like prior to coming here. Right. So maybe I'll jump down to the slides about projects going on here. Why am I not getting my slides here? So let's see. Okay, so one of the projects involves taking tensor product representations for syntactic trees, dependency parsers, and mapping them into tensor product representations for graphs in the formalism of AMR for the meaning of the sentences. And we're interested in learning the transformation between them. And I'm interested in learning the vectors that are used to encode the symbols and their roles in the structures. But so far, we haven't done any of the learning work yet. The algorithms are waiting, but they're not tried yet. And we use the same representational scheme as I indicated before for representing these two types of graphs by representing all the triples in them and superimposing them, adding them together. Sorry, microphone, I guess I shouldn't touch my shirt. And to have some kind of neural network that does the mapping from one tensor product representation to the other is what we're shooting for. But my boss would only allow me 20 dimensions, and I have 15,000 symbols. So after I stopped cursing him, I started looking into the question of, well, if you only can afford 20 dimensions, what can you do in generating 15,000 vectors to represent 15,000 words, which appear in the corpus of inputs and outputs for this task? And here's a picture of what happens when you try to minimize a function here, which penalizes large dot products for vectors. So what we have here is a plot of the resulting vectors from an example run. And what you see is that there are 15,000 vectors, each 20 numbers long. And the biggest dot product between two of them, two different ones, is 0.72. So that means that the dot product, you remember that when we try to do unbinding, we really want the vector that is binding a particular position we're interested in to have the property that when you take its dot product with itself, you get 1, and when you take its dot product with all the others, you get 0. So wipe out all the other constituents that you're not going after. So what we get here instead is we get a 1, just because we choose them to be normalized, but for the dot product of the roll vector with itself. But we get as big, up to about 0.7 something for all of the other rolls that we are actually trying to exclude. So that constitutes the noise that we have in the representation because we don't have linearly independent roll vectors.
So you're solving for V's and beta here?
What's that?
You're solving for Vj, Vk,
Oh,
and beta.
no, sorry. I just fixed beta. Yeah.
So there must be constraints, because I could make Vj dot Vk
Yeah.
huge and negative.
So they're all normalized vectors. So you can try to make them negative, but you can't make them huge.
And there's no notion of similarity, semantic similarity between the vectors, or there?
Right, so this is a case where we're trying to make things as orthogonal as we can, but in other situations we would want to rather to impose some. And so one of the interesting things about learning is once the network mapping syntax to semantics can influence the choice of these things, will it prove helpful to make similar the vectors for certain pairs of symbols or pairs of rolls for that matter. So that's one of the projects.
Is there any way to maybe add coordinates as you go along? Like, just keep the dimensionality small, but when you need to disambiguate among things at a higher level, you add temporarily more sort of features, more like hashing values almost. So that your vector is you actually never fully represent the full vector.
Right. I haven't pursued that line of inquiry yet, but it's interesting. I don't think what I have pursued is what you have in mind, but it certainly is close, if not the same. And that is, we really want the, so the idea is to have a purely hypothetical space of dimension 15,000 here for each of the orders of the tensor. And then to do something like principal components analysis over the set of vectors that we are really trying to process, to pull out a lower dimensional subspace that's more manageable. And that can be done incrementally as examples are processed. So that we haven't started on carrying that out. I have an algorithm, but I don't have any experience with it. Yeah. Yeah.
Started with dependency analyses.
Well, they're dependency trees.
They're not
Yeah.
constituents.
They are. They're just dependency parses.
So these are coming from the Stanford parser.
Yeah, either a Stanford parser or an Illinois parser. But the idea is that we're helping ourselves to using standard symbolic means for taking the input string and producing some kind of parse of it. And for our purposes, of course, the more the structure in the syntax mirrors the structure in the semantics, the better we are. The better our chances are for being able to readily implement the mapping between them. So some people have used CCGs for this purpose. Yeah.
So the dimensions of 20, what does that represent? Is that like a constraint on real-time hardware, single GPU?
You know Lee better than that. We need 20 dimensions for A, another 20 for B, so we're up to 400. And then we have 10 for R, and that's 4,000. So the overall dimensionality that we get is 4,000. So part of the reason that we have to be very skimpy here is that it gets squared along the way. But another fact is that we don't have the World Wide Web as our database. We have 10,000 example pairs to work with. So the number of parameters in the network that's mapping from one to the other, because we have 4,000 input, 4,000 output, 16 billion connections, and 10,000 examples to train them on. And so there are various considerations aside from sheer computational cost that also mean that if we are too profligate in the representations, then we won't expect to generalize well beyond training set. Yeah.
15,000, is that on the input side or the output side?
Well, the number actually after I did this went up to 15,500, and that was the union of the two.
There are a lot of tokens on the input side that never show up on the output side.
Well, this number is coming down as we speak. So the intern working on this is doing named entity recognition and replacing all the proper names with just a single symbol. And so that number is going to go down, and that will reduce the amount of noise that we have to cope with a lot. Let's see, so another task and one idea for it, this isn't the original idea from the intern, but it's a more straightforward way of using tensor product mechanisms to do it, is a task that Facebook put together and has gotten a certain amount of attention for reasons that are somewhat mysterious to me, but it has. The idea is to code things in a relational format and use this exact mechanism of just binding together by the outer product the relation and its arguments. So here's what the task looks like. Let me see if I can do anything useful about being able to read these things. So there's some sort of old-fashioned adventure game world for generating sequences of happenings that get expressed in simple sentences. And so you get a sentence like, John promised a baseball to K, Jay gave a baseball to L. So you get a bunch of sentences in some sequence, and at various points during that sequence, you have to answer questions like, what did Jay give to K? Or where is the football? Or things like that. So there's a supposedly increasingly difficult series of types of questions to for your program to have to answer. So here, so the example is, what did J give K? So the approach here is to translate these things in a pretty straightforward way into a logical form that is called Neo-Davidsonian by some people in linguistics, where we have these event variables and properties of events, like this is a promising type event that's being described here, and that event has as its agent J, very, very straightforward, simple things. But the point is that as soon as we write it this way, then we can use the mechanism I just described and have tensor product representations up the wazoo for all of these predications, and we add together the information in multiple sentences, and then we query, oops, there they are, now they're back. We query, so the question was, what did J give K? So we have one tensor which has all this information from these 4 sentences, and we do some querying to figure out what event is a giving event in which the agent is J and the recipient is K, and having identified that event, then what is the theme in that event, and that's the thing that was given. So anyway, we use outer products. I haven't rewritten this slide to get rid of all the tensor product signs, but so that's in the works. We don't have results. What's that?
How do you figure out where the ball is?
How do you figure out where it is?
Yeah.
You well, you have to find some kind of event that is in a class of events that localize something and query for events of that type. And what this simple scheme does not do, which needs to be done for that type of question really, is to tag events with times so that you can keep track of something being in multiple places as the story progresses. And then I don't know how it is we're going to be able to simply determine the most recent time that, you know, the event that is most recent that identifies the location of this object. I'm not sure how to do that, but
Just ask is, what did J give K? How are you going to solve that? Do you
what did J give K?
unbind the, because you've now got, you know, there's a relation giving between J and, I mean, give is a three-place predicate.
Well, in Neo-Davidsonian terms, we only have these triples. So there isn't a proposition that has both J and K in it. There are two propositions that say J is the agent of event 1 and K is the recipient in event 1. So you have to be able to cope with that, which makes certain things harder, right? Not easier.
But you want to unbind such that you recover the theme.
Yeah. So you do some unbinding to determine what event is the relevant event, which is the giving event that has this agent and that recipient. And once you've found the event, then you probe the tensor representing the story to find out in that event what element is bound to the theme role, which is what is given. That's the name for that's the name I chose for what gets given. So you unbind theme for that event.
And then where in the representation of what do you know that that's how you're going to do the unbinding?
I guess you have to translate this sentence into the form, return the theme of the event, which is of type giving and has agent J and patient K. You have to translate it into that somehow. Yeah. Right. So anyway, again, we have relatively high order tensors here. So the number of dimensionality of the vectors that encode these is going to be the product of the dimensionality of these three types. And so we're also going to have a challenge of putting a lot of triples of symbols, many different types of triples of symbols into some manageable size vector space. So let me see if there's any kind of sensible conclusion here for, let me just mention this for the what we have for reverse engineering, because I was really hoping to get some of this done here. I'm just going to have one slide and then I'll promise I'll stop. So we have a machine learning approach using a generative model to address the following problem, and I would like to try to use it on networks that have been trained to produce English output and try to analyze the representations in the hidden layers of these networks with this tool. So the problem that this tool addresses is you're given a set of vectors which are, let's say, the states of a hidden layer in a deep neural network, although we're also going to try to do it for activation patterns in neural recordings. And different of these vectors correspond to different inputs. You know what input corresponds to each of these states of the hidden layer, let's say. You want to interpret them in order to be able to say how they are encoding the domain data to the point where you can actually explain how it succeeds in finding the output for the input using these intermediate representations. And the hypothesis that this pursues is that the vectors that you're given here at the top are actually tensor product representations unbeknownst to anybody. And so you have a generative model which produces tensor product representations using choices for what the roles and fillers are for each of the inputs and what vectors encode each type of role and each type of filler. And those will have to be fit in the learning process in order to account for, maximize the likelihood of the set of vectors that you received as your starting point. Standard kind of a generative model and techniques, standard techniques, have been implemented and tried on some synthetic data with partial success. But I'd like to see whether anything useful can come out of it applied to actual hidden layers for networks that do things in language which we need to understand and which we have some information from linguistics about what might be in the representations to make it possible for some system to correctly produce those kinds of sentences. And I think I will stop right there. Thank you for your patience. So, 2 minutes left before noon. No parting question?
So we had a presentation of the Facebook data set. So what are some results? Do you have some results?
We have not implemented what I showed you yet. The intern who was working on it implemented a much more special purpose approach, which had a lot of the similar ideas buried in it, but not in such a generalizable form. And he claims to be able to answer 18 of the 20 types of questions at this point, at last report.
You want to do
I believe that's the claim, yeah, yeah.
Cool.
But how hard it is to do that, making all of the assumptions that are being made, I don't really know.
So that's the Babby data set, right? It's
Yeah,
the
yeah.
synthetic data.
Yeah, yeah.
So just in case you're curious, we have a data set that's not synthetic, that's fictional stories with questions that I can point you to if you're curious.
Oh, okay, yes.
It's public.
These are not synthetic fictional stories?
No, it's this MC test, it's 500 short stories, short fictional stories with multiple choice questions.
Right, multiple choice question. I'm about to learn about those.
Hmm?
I'm about to learn more about those. Chris has sent me some stuff. Yeah. All right, well, Friday I'll try to say something more interesting from a linguistics/language point of view. Thank you.